atmospheric circulation. As the sun beats down and the ocean warms, water from the upper layer of the ocean evaporates. The conversion of liquid to vapor requires a lot of energy, so evaporation cools the top layer. Think of how sweat evaporating from your skin cools your body. Trade winds then carry the vapor to the area where the north and south trade winds converge, called the Intertropical Convergence Zone, or ITCZ. There, the moist air rises and cools. The water vapor condenses on tiny particles suspended in the air called nuclei, forming clouds. This condensation releases energy, heating the surrounding air. The warmed air then rises even higher, drawing up more moisture from the ocean. More vapor then condenses higher in the atmosphere and releases more heat, causing the air to rise further, and so on. The result is towering clouds that dump up to 5 meters of rain per year over some parts of the tropical ocean. There's a diagram of the fast carbon cycle that shows the movement of carbon between land, atmosphere, and oceans. Yellow numbers are natural fluxes and red are human contributions in gigatons of carbon per year. White numbers indicate stored carbon. The diagram is adapted from the US DOE Biological Environmental Research Information System. Now, carbon flows between each reservoir in an exchange called the carbon cycle, which has slow and fast components. Any change in the cycle that shifts carbon out of one reservoir puts more carbon in other reservoirs. And changes that put carbon gases into the atmosphere result in warmer temperatures on Earth. This same process fuels hurricanes. At the centers of these storms, moist air rising from the warm ocean heats up as the water vapor condenses. And then, since warm air is less dense, the atmospheric pressure drops. More moist air then rushes in off the ocean due to the pressure gradient, rotating counterclockwise due to the Coriolis effect. This air rises up and condensation releases more heat, intensifying the storm and further lowering the pressure. Hurricanes generally don't form close to the equator because the Coriolis effect is weak. Now, taking a global perspective is important. What happens in oceans on the other side of the globe certainly affects us wherever we are. As National Geographic pointed out in a March 2019 article, quote, "Since warm ocean waters are essential to form and maintain a hurricane, scientists wondered if there was a connection between warmer ocean temperatures and an increase in hurricane frequency and strength. Scientists have been examining the effect of climate change on sea surface temperatures around the globe, using records from as far back as 1880. The data shows a significant surge in global sea surface temperatures, and researchers suspected that climate change was playing a part in these warmer waters, but they needed to find proof." Now, Ethan Gutman, a project scientist at the National Center for Atmospheric Research, found a way to show how climate change would affect hurricanes.